Hi there, welcome in. I'm so glad you made it here today. Before we get started, I'd love to hear where you're tuning in from and what time it is for you. It's such a treat to see the variety of places and times represented in this community. I also want to gently thank those who have subscribed and clicked like on the videos they enjoy. It really helps this space grow. And of course, if you have ideas for new content, I'd love to hear them in the comments. With that, let's begin. Chapter 1: Understanding Sound Waves and Frequency. Sound is an omnipresent force, an invisible wave that fills our environment with a rich tapestry of experiences. It is the gentle rustle of leaves in the wind, the soothing trickle of water in a stream, and the vibrant symphony of voices that tell our stories. But what exactly are sound waves? At their core, sound waves are vibrations that travel through a medium, whether that be air, water, or solid materials. These vibrations create pressure changes that move through the medium, forming waves that can be detected by our ears. Sound waves can be classified into two primary types: longitudinal and transverse. Longitudinal waves are the most common in sound, where the direction of the wave's vibration is parallel to the direction of the wave's travel. Imagine a slinky toy being pushed and pulled along a surface. The coils compress and expand in the same direction as the wave moves, creating areas of high and low pressure. In contrast, transverse waves, which are less common in sound, feature vibrations that occur perpendicular to the direction of travel. An example of this can be seen in waves on a string, where the motion goes up and down while the wave travels horizontally. Each sound wave possesses distinct properties that define its character. The amplitude of the wave refers to its height, which influences the loudness of the sound we perceive. A wave with a larger amplitude is heard as louder, while one with a smaller amplitude is softer. The frequency of a sound wave, measured in hertz, indicates how many wave cycles pass a point in 1 second. This frequency is fundamentally linked to the pitch of the sound we hear. Higher frequencies correspond to higher pitches, while lower frequencies produce deeper, richer tones. To visualize frequency, imagine a calm lake. When a stone is tossed into the water, it creates ripples that radiate outward. The closer together these ripples are, the higher the frequency. As they spread out, the frequency decreases. The distance between two consecutive wave peaks is known as the wavelength. A shorter wavelength indicates a higher frequency, while a longer wavelength signifies a lower frequency. This relationship between frequency and wavelength is crucial. It helps us understand how different sounds are perceived and experienced. The importance of sound wave frequency in audio perception cannot be overstated. Our ability to differentiate between sounds relies heavily on their frequencies. For instance, a piano and a violin playing the same note can produce distinctly different qualities due to their unique harmonic structures and the frequencies they emphasize. When we listen to music, we engage with these frequencies, allowing us to experience emotions, create memories, and connect with one another at a profound level. Renowned physicist Albert Einstein once said, "Everything in life is vibration." This statement resonates deeply with our understanding of sound. The frequencies of sound waves not only affect how we hear, but also influence our emotional responses. Researchers have shown that certain frequencies can evoke specific feelings or states of mind. For example, low frequencies, often found in the music of orchestras, can create a sense of calm or even melancholy, while higher frequencies can inspire excitement or happiness. Imagine walking into a vibrant concert hall, where the air is filled with the rich sounds of an orchestra tuning up before a performance. Each instrument, from the cellos to the flutes, produces a unique frequency, and together they create a complex auditory landscape. As the conductor raises their baton, the sound waves harmonize, creating a rich tapestry of music that resonates deep within us. This experience highlights how frequency plays a pivotal role in our appreciation of sound and music. As we explore further, we can also consider the remarkable work of pioneers in the field of acoustics. One such figure is Hermann von Helmholtz, a German physicist and physician who made significant contributions to our understanding of musical tones and harmonics. Helmholtz's experiments revealed that complex sounds can be broken down into simpler components, each with its own frequency. He famously stated, "The ear is a very delicate instrument, which has to be trained to detect the different tones of sounds." This speaks to the importance of frequency, not only in the creation of sound, but also in our ability to perceive and appreciate it. The human ear itself is an extraordinary organ, intricately designed to detect a wide range of frequencies. It can perceive sounds from as low as 20 Hz to as high as 20,000 Hz. This range, however, tends to decrease with age, which is a natural part of human development. The ear consists of three main parts: the outer ear, middle ear, and inner ear. Sound waves enter through the outer ear, travel down the ear canal, and cause the eardrum to vibrate. These vibrations are then transmitted through tiny bones in the middle ear, known as the ossicles, before reaching the inner ear, where they are converted into electrical signals and sent to the brain for interpretation. Imagine the delicate process occurring within your ear as you listen to a gentle breeze rustling through the trees. The sound waves travel seamlessly, transforming into signals that your brain interprets as the soothing melody of nature. This remarkable ability to transform vibrations into meaningful auditory experiences is a testament to the complexity and beauty of sound. Understanding sound waves and frequency enriches our comprehension of the world around us. They connect us to our environment, allowing us to experience the beauty of nature, music, and communication. Our perception of sound is not merely a biological function. It is a deeply emotional and sensory experience that shapes our lives. The next time you hear a gentle rain tapping against your window or the laughter of a loved one, take a moment to appreciate the intricate web of frequencies and vibrations that make those moments possible. The journey into the realm of sound is a captivating one, filled with wonder and discovery. As we explore the nuances of sound waves and their frequencies, we begin to appreciate the profound impact they have on our lives, guiding our emotions, enhancing our experiences, and connecting us to one another in ways that words alone cannot express. The ability of sound waves to influence not just our auditory perception, but also our emotions is a fascinating aspect of human experience. Consider the phenomenon of binaural beats, where two slightly different frequencies are played in each ear. This creates an auditory illusion that the brain interprets as a single tone, which can have a profound effect on mental states. By listening to these carefully crafted soundscapes, individuals often report feelings of relaxation, focus, or even heightened creativity. Imagine yourself in a quiet room, wearing headphones, as soft, rhythmic beats wash over you. The sound gently nudges your brainwaves into a state of calm, perhaps inviting a moment of reflection or meditation. This intricate dance between sound and the brain illustrates the power of frequencies in shaping our mental landscape. Moreover, the science of sound has applications that extend beyond personal experiences. The field of sound therapy has emerged, harnessing the healing potential of sound waves to promote well-being. Practitioners use specific frequencies and rhythms to create a sonic environment conducive to relaxation and healing. Certain frequencies, like those around 400 Hz, are believed to resonate with the body in a way that fosters healing and balance. Have you ever noticed how some songs make you feel uplifted, while others leave you contemplative. This emotional response is tied directly to the frequencies and harmonics present in the music. Artists often manipulate these elements to evoke specific feelings in their listeners. The bass notes in a piece of music can ground us, while higher frequencies can elevate our spirits. It's a remarkable interplay, one that musicians and composers have explored for centuries. Take, for example, the works of renowned composer Johann Sebastian Bach. His intricate compositions are celebrated not only for their complexity, but also for their ability to convey deep emotions. Bach understood that certain harmonic progressions and frequencies could evoke a spiritual response in his audience. His music serves as a timeless reminder of how sound can transcend mere auditory experience and touch the very essence of our being. As we engage with sound, it is also essential to consider how our environment shapes our auditory experiences. Natural settings, such as forests or mountains, provide distinct soundscapes that differ greatly from urban environments filled with the hum of machinery and chatter. The acoustics of a space can influence how we perceive sound, affecting its richness and clarity. Imagine standing in a vast, open field, surrounded by the gentle sounds of nature. The rustling leaves create a soft, enveloping sound that seems to harmonize with the distant chirping of birds. This serene atmosphere invites a sense of peace and connection to the world around you. In contrast, think of the bustling streets of a city where myriad sounds collide: honking cars, distant sirens, and the chatter of passers-by. Here, the experience of sound becomes a cacophony, often overwhelming rather than soothing. The relationship between sound and space also leads us to consider the fascinating concept of acoustics. Acoustics, the science of sound, examines how sound waves interact with different environments. It influences everything from concert halls to recording studios. Architects and sound engineers work meticulously to design spaces that enhance sound quality, ensuring that each note played or spoken word resonates beautifully. Consider the Sydney Opera House, a masterpiece of architectural design. Its unique structure not only captivates the eye, but also shapes the sound within. The building's curves and angles create an auditory experience that delights both performers and audiences alike. Each performance is a collaboration between the musicians and the space, highlighting how acoustics can elevate the art of sound. In addition to architecture, the study of sound waves has led to remarkable technological advancements. Innovations such as noise-canceling headphones and advanced sound systems showcase our ability to manipulate sound waves for enhanced listening experiences. Imagine the quiet calm of a busy city melted away by the soothing sounds of your favorite music, the outside world fading into a distant memory. This is the power of sound technology, allowing us to curate our auditory environments intentionally. As we continue to explore the depths of sound and frequency, we find ourselves on a journey that touches not only the ears, but the heart and mind. Each sound wave carries with it a story, a connection to the world around us. From the soothing hum of a lullaby to the invigorating beats of a dance track, sound waves shape our lives in ways that are both profound and intimate. What if we took a moment to reflect on our personal soundscapes? The sounds that accompany your daily life, what do they evoke for you? Are they familiar, comforting, or perhaps even unsettling? By tuning into these auditory experiences, we can begin to appreciate the subtle yet powerful role that sound waves play in our emotional and psychological well-being. In this exploration of sound waves and frequency, we uncover a rich world filled with possibilities and profound connections. Sound is not merely an auditory phenomenon. It is a universal language that transcends barriers, uniting us in our shared experiences. Each frequency, each vibration, is an invitation to listen more closely, to engage more deeply, and to connect more authentically with ourselves and others. As we immerse ourselves in this realm, we are reminded that sound is all around us, waiting to be discovered, understood, and cherished in its myriad forms. Each sound wave is an opportunity for exploration, a chance to connect with the vibrant symphony of life that surrounds us. So, let us continue this journey together, embracing the beauty and complexity of sound and frequency as we move forward. Chapter 2: Introducing the Doppler Effect Concept. The Doppler effect is a remarkable phenomenon that has captured the curiosity of scientists and laypeople alike for over a century. Its discovery traces back to a humble Austrian physicist named Christian Doppler, who first proposed this concept in 1840. Imagine him standing in a bustling square, observing the world around him. As the sound of a train approached, he noted how the pitch of its whistle changed as it drew near and then receded. Inspired by this observation, Doppler articulated what would become a foundational principle of wave mechanics. His insight revealed that the frequency of a wave changes depending on the relative motion between the source of the sound and the observer. Picture yourself in a serene park, the gentle hum of distant traffic intermingled with the songs of birds. As a police siren approaches, you hear the high-pitched wail growing louder, only to dip to a lower tone as it passes by. This auditory experience is the essence of the Doppler effect in sound. The sound waves emitted by the siren are compressed as the vehicle moves toward you, increasing the frequency and resulting in a higher pitch. Conversely, as the vehicle moves away, the waves stretch out, decreasing the frequency and creating a lower pitch. This shift in frequency is a vivid reminder of the complex interplay between motion and sound, one that we encounter in our daily lives without even realizing it. Understanding the Doppler effect requires an appreciation of relative motion. It is not merely the speed of the sound waves themselves that matters, but rather the speed at which the source of the sound and the observer are moving in relation to one another. If you were to stand still while a sound source moved toward you, you would perceive a different frequency than if you were moving toward the source as well. This principle can be visualized by considering two trains on parallel tracks. If one train is stationary and the other is zooming past, the sound waves produced by the moving train will reach the stationary observer at a higher frequency. However, if both trains are in motion, the situation becomes more intricate, as each train's speed affects the sound waves perceived. The implications of the Doppler effect extend beyond the realm of everyday experiences. This phenomenon has become a critical tool in various scientific disciplines. Astronomers, for instance, rely on the Doppler effect to understand the movement of celestial bodies. When light from distant stars shifts toward the red end of the spectrum, it indicates that those stars are moving away from us, a concept known as redshift. Conversely, a blue shift occurs when stars move closer. This application of the Doppler effect has provided profound insights into the expanding universe, as articulated by the famous physicist Edwin Hubble, who stated, "Equipped with his five senses, man explores the universe around him and calls the adventure science." Consider the vastness of space and how the Doppler effect allows us to infer the motion of galaxies billions of light-years away. Each shift in frequency tells a story, revealing the dance of cosmic forces and the expansion of the universe itself. It connects us to a time and place far removed from our own, yet it is rooted in the same principles that govern our everyday experiences with sound. Reflecting on the historical context of Christian Doppler's discovery, it is remarkable to note how a simple observation led to a profound understanding of wave mechanics. At the time, Doppler was exploring the interplay of color and sound, believing that the principles governing one might illuminate the other. His hypothesis was a bold leap, bridging the realms of physics and perception. The Doppler effect is not limited to sound. It also extends into the world of light and electromagnetic waves. Just as the frequency of sound waves shifts with relative motion, so too does the frequency of light waves. This duality illustrates the universal nature of the phenomenon as it applies to different types of waves, enriching our understanding of the physical world. Imagine a scenario where you are standing on a hillside, watching a helicopter approach. As it nears, the rotors create a rapid, high-pitched whirring sound. As it passes overhead and begins to recede, that sound shifts dramatically, deepening into a resonant thrum. This auditory transformation is the Doppler effect at work, illustrating how sound waves compress and stretch depending on the relative motion of the source and observer. In medical applications, the Doppler effect takes on a life-saving role. Doppler ultrasound is a technique used to assess blood flow in patients. By emitting sound waves into the body and analyzing the frequency shifts of the echoes that return, medical professionals can determine how efficiently blood is circulating. This non-invasive approach has revolutionized diagnostics and treatment, providing critical insights into cardiovascular health without the need for more invasive procedures. As we ponder the importance of relative motion in the Doppler effect, it raises intriguing questions about our perception of reality. How often do we overlook the nuances of our surroundings, the subtle shifts in sound that tell us about the movement of objects nearby? The world is in constant flux, and the Doppler effect serves as a reminder of the dynamic nature of our environment. Consider the implications of this principle in your own life. When you hear the distant sound of a train or the siren of an emergency vehicle, think about the intricate dance of sound waves and motion unfolding around you. It's a beautiful interplay that shapes our auditory experiences, painting our world in layers of frequency and pitch. In the realm of physics, the Doppler effect serves as a gateway to deeper explorations of wave behavior. It invites students and enthusiasts alike to engage with concepts like frequency, wavelength, and amplitude, fostering a richer understanding of how sound travels through different mediums. As we continue to unravel the mysteries of sound and its interactions with motion, the Doppler effect stands as a testament to the power of observation and inquiry. It reminds us that every sound we hear carries with it a story of movement and change, a narrative waiting to be uncovered. In exploring this phenomenon, we not only deepen our comprehension of sound and light, but also cultivate a sense of wonder for the universe that envelops us. Each shift in frequency, each change in pitch, reveals the intricate connections between the observer and the observed as we navigate a world filled with vibrational symphony. As we immerse ourselves in the fascinating world of the Doppler effect, it is essential to recognize the historical significance of its discovery. Christian Doppler's original proposal was not merely a scientific curiosity, but a pivotal moment that altered our understanding of waves. His insights laid the groundwork for future explorations in various fields, from optics to astrophysics. Imagine the excitement that must have accompanied the realization that sound and light could be influenced by the motion of their sources. This discovery echoed throughout the scientific community, inspiring others to investigate the profound implications of wave behavior. In the context of sound, the Doppler effect becomes even more intriguing when we consider its applications in technology and everyday life. For instance, modern radar systems utilize this principle to measure the speed of objects. When radar waves bounce off a moving vehicle, the frequency of the reflected waves changes depending on the vehicle's speed and direction. This application is vital for law enforcement and traffic management, demonstrating how a scientific principle from the past has found relevance in contemporary society. Imagine standing on a busy street where cars whiz by, each accompanied by the familiar sounds of their engines. As you listen closely, you may notice that the sounds change as they approach and then move away. This auditory phenomenon is not just a trick of the ear. It is the Doppler effect in action, subtly reminding us of the relationship between motion and sound. In the realm of astronomy, the Doppler effect unveils the mysteries of the cosmos. Astronomers analyze the light from distant stars and galaxies to determine their motion relative to Earth. A star moving away from us will have its light shifted to longer wavelengths, creating a red hue, while a star approaching us will exhibit a blue shift, indicating a shortening of its wavelengths. This shift serves as a cosmic beacon, guiding our understanding of the universe's structure and expansion. The realization that the universe is in constant flux, with galaxies racing away from each other, can be both humbling and awe-inspiring. Consider the words of famous astrophysicist Neil deGrasse Tyson, who noted, "The universe is under no obligation to make sense to you." This sentiment resonates deeply when we reflect on how the Doppler effect allows us to piece together the cosmic puzzle. By studying the light emitted from celestial bodies, we can glean insights into their velocity, composition, and distance, painting a broader picture of the cosmos. As we explore these vast distances, the importance of relative motion becomes even more pronounced. It is not only the motion of the observer that matters, but the motion of celestial entities that shapes our understanding of their behavior. For example, when we observe a binary star system, where two stars orbit each other, the Doppler effect allows us to measure their velocities through the shifts in their spectral lines. This information sheds light on their mass, distance, and even the gravitational forces at play, culminating in a clearer understanding of the dynamics of such systems. Within the medical field, the Doppler effect showcases its utility in an entirely different light. In Doppler ultrasound, sound waves sent into the body can detect blood flow, providing critical information about cardiovascular health. By analyzing the frequency shifts of the returned waves, healthcare professionals can assess the speed and direction of blood flow, leading to timely interventions. This non-invasive technique has revolutionized diagnostics, allowing for early detection of issues like arterial blockages or heart valve problems, ultimately saving lives. Consider the implications of this technology in the context of patient care. Imagine a doctor using Doppler ultrasound to monitor a developing fetus, ensuring its health and well-being. This application exemplifies how the principles of the Doppler effect extend far beyond theoretical physics, influencing real-world outcomes in healthcare. As we contemplate the broader implications of the Doppler effect, it invites us to consider how our perceptions are shaped by the world around us. Have you ever noticed how the sounds of nature change with the wind? The gentle rustling of leaves can transform into a cacophony when a breeze picks up, while the distant sound of thunder may grow ominous as it approaches. These shifts are not only a testament to the Doppler effect, but also a reminder of the interconnectedness of all phenomena in our environment. The Doppler effect stands as a powerful illustration of how motion influences our perceptions, shaping our auditory experiences in subtle yet profound ways. It encourages us to tune into the world, to listen closely to the melodies of our surroundings, and to appreciate the intricate interplay of sound and motion. In the vast expanse of scientific inquiry, the Doppler effect serves as a bridge, connecting our everyday experiences with high-level scientific exploration. It allows us to perceive the universe not just as a static backdrop, but as a dynamic landscape where waves of sound and light constantly interact. The more we understand these principles, the more we appreciate the intricate designs woven into the fabric of reality. As we continue to explore the nuances of the Doppler effect, it becomes clear that this concept is much more than a mere scientific principle. It embodies a journey of discovery, inviting us to ponder the nature of waves and motion and their roles in shaping our understanding of the universe. With each shift in frequency, we are reminded of the beauty and complexity that lies beneath the surface, waiting to be uncovered. Chapter 3: Observing the Doppler Effect in Action. Imagine standing on a quiet street, the air still and filled with anticipation. Suddenly, you hear the unmistakable sound of a vehicle approaching. As it draws nearer, the piercing wail of a siren fills your ears, a sound that grows in intensity and pitch. The moment it passes you, the tone shifts dramatically, fading into a lower, distant echo. This experience is a daily demonstration of the Doppler effect, a phenomenon that transforms how we perceive sound and movement in our environment. As the vehicle speeds towards you, the sound waves compress. Picture the waves as a series of tightly packed spring coils, each representing a moment of sound. The closer the vehicle gets, the more these coils bunch together, creating a higher frequency. This increase in frequency leads to that sharp, urgent sound of the siren, compelling your attention. Now, as the vehicle passes and begins to move away, the sound waves stretch out. Imagine those spring coils now being pulled apart, the distance between them increasing. The frequency decreases, resulting in a lower pitch that gently fades into the background. This auditory transition illustrates the essence of the Doppler effect, an everyday experience that connects us to the principles of wave mechanics. To delve deeper, consider the science behind frequency changes for moving sources. The frequency of a sound wave is determined by the vibrations produced by its source. When the source is stationary, the sound waves travel in a uniform pattern, reaching the observer with a consistent frequency. However, when the source is in motion, that pattern shifts dramatically. As the source approaches, the sound waves bunch together and the frequency increases. Conversely, as it moves away, those waves elongate, resulting in a decrease in frequency. This change is not merely a matter of perception, it is a physical reality rooted in the laws of wave propagation. Think of how this principle applies not only to sirens, but also to the sounds of nature. Picture a train gliding down the tracks, its whistle echoing across the landscape. As it approaches, the high-pitched sound calls to you, a siren's song drawing you closer. As the train passes, the sound transforms, the once sharp whistle morphing into a distant hum. This transformation happens because the sound waves are emitted at a constant rate, yet their interaction with the moving train alters their frequency. The train, in this case, is the source of sound, and as it travels toward you, the waves compress, creating that heightened sense of urgency in the sound. Now, let us consider the role of the observer. The experience of the Doppler effect is not solely dependent on the source's motion. The observer's position plays a crucial role as well. Imagine standing still as a vehicle speeds past. You are stationary, absorbing the changes in pitch as the waves collide with your ears. But what happens when the observer is in motion? If you were to run alongside the vehicle, your experience would be quite different. As you chase the siren, the frequency would remain relatively constant, as both you and the vehicle are in motion toward a common point. This raises an intriguing question. How does the perspective of the observer shift the auditory experience of sound? The beauty of the Doppler effect lies in its ability to illustrate the connection between sound waves and movement, both of the source and the observer. It invites us to ponder the nature of sound itself. Are we merely passive listeners, or do our movements shape our auditory landscape? The powerful implications of the Doppler effect stretch beyond our everyday experiences. In the realm of astronomy, it serves as a critical tool for understanding the cosmos. When we observe distant stars and galaxies, the light they emit experiences similar frequency changes due to their motion relative to Earth. The shift in light frequency, known as redshift or blueshift, depending on whether the object is moving away or towards us, provides valuable insights into the universe's expansion. Consider the profound words of a renowned astrophysicist who once said, "The universe is expanding, and we are living in a time of discovery." This expansion is not merely a concept. It is a reality observable through the lens of the Doppler effect. Just as a passing vehicle alters the sound around us, so too does the movement of celestial bodies shift the light we perceive. As we explore these ideas, let your imagination wander. Picture standing on a tranquil hillside, gazing at the night sky. The stars twinkle like distant lanterns, each one a world unto itself. Now, envision that some of these stars are moving toward you, their light shifting to a higher frequency, while others glide away, their light stretching to lower frequencies. This interplay of motion and perception invites us to appreciate the universe's complexity. In our everyday lives, we witness the Doppler effect in action through various scenarios. Think about the sounds of a race car speeding by at a track. As the car accelerates towards the grandstand, the roar of its engine crescendos, a thrilling rise in pitch that captures the excitement of the moment. Then, as it speeds past and continues down the track, the sound dips, leaving behind a fading echo. This is not only a spectacle of speed, but a vivid demonstration of the principles of wave mechanics we have explored. The race car, much like the siren, serves as a moving source, altering our auditory experience. Now, reflect on how this concept can be applied beyond just sound. In the world of medical imaging, the Doppler effect plays a vital role in ultrasound technology. Physicians use ultrasound to visualize organs and blood flow in the body. When sound waves are emitted towards moving blood cells, the frequency shifts based on their movement. This allows doctors to assess circulation and detect potential health issues, transforming the Doppler effect into a tool for healing. The versatility of the Doppler effect demonstrates its far-reaching implications, impacting various fields from astronomy to medicine. Each instance serves as a reminder of the extraordinary nature of sound and the waves that connect us to the world around us. As we draw this chapter to a close, consider the rich tapestry of experiences shaped by sound waves and the motion of sources and observers. The Doppler effect reveals the unseen connections that bind our auditory experiences to the rhythms of life. In each sound, there lies a story, a journey of waves traveling through space and time, inviting us to listen more closely to the world that envelops us. As we observe the intricate relationship between sound and motion, let's consider a moment that many of us have experienced, the sound of a passing train. The powerful locomotive thunders down the tracks, and as it approaches, the sound of its horn resonates through the air, a powerful, piercing note that commands our attention. This auditory experience is a direct consequence of the Doppler effect in action. When the train approaches, the sound waves emitted from its horn travel toward us, compressing in the process. Imagine standing on the platform, feeling the vibrations in your chest as the high-pitched sound reaches you. This is not just an auditory phenomenon, it embodies the physical principles of wave propagation. The train, moving at a considerable speed, alters the frequency of sound waves, creating a sense of urgency and excitement that fills the air. But what occurs as the train passes by? The sound transforms, the once sharp whistle morphing into a deep rumble that fades into the distance. This is the moment when the waves begin to stretch, illustrating the fundamental aspect of the Doppler effect. The frequency decreases, and the sound that once pierced the air becomes a gentle echo, a reminder of the train's passage. In this scenario, the observer's position is pivotal. Standing still, you experience the full spectrum of the sound's transformation. But imagine if you were on a bicycle, pedaling alongside the train. The experience would shift dramatically. As you move at a similar speed, the frequency of the sound remains relatively constant, presenting a unique auditory experience. This interplay between the source and the observer emphasizes how our perception of sound is influenced by movement and proximity. The exploration of frequency changes leads us to consider other everyday examples. Consider the blaring horn of a car as it races down the street. Much like the train, the car induces a dramatic shift in sound perception as it approaches and departs. The urgency of the sound as it nears is palpable, and the subsequent drop in pitch as it moves away can evoke a sense of calm, as if the world has momentarily paused. This principle extends beyond mere observations of vehicles. Let us delve into the world of sports, where the Doppler effect can amplify the thrill of the game. Picture the sound of a soccer ball being kicked down the field. As players sprint toward the goal, the sound of the ball slicing through the air creates a dynamic auditory landscape. The sound waves shift as the ball travels, compressing as it approaches the goal and elongating as it moves away. The excitement builds with each kick, and the crowd's collective gasps and cheers intertwine with the changing sounds, creating an immersive experience that resonates in our memories. In the realm of science, the implications of the Doppler effect are profound. It serves not only as a phenomenon we encounter in our daily lives, but also as a tool for understanding the universe. Astronomers utilize the Doppler effect to study the movement of celestial bodies. When we observe the light emitted by distant stars, we notice shifts in color that reflect their motion. This redshift, when stars move away from us, allows scientists to infer the rate at which the universe is expanding. Conversely, blue shift occurs when stars move toward us, their light compressing into a higher frequency. The beauty of this discovery lies in its simplicity and its depth. Imagine gazing at the night sky, contemplating the vastness of the cosmos. The stars above, with their shimmering light, tell a story of movement across the universe, a cosmic ballet that has been unfolding for billions of years. As we explore these celestial phenomena, we engage with the very essence of the Doppler effect, a bridge connecting our earthly experiences to the mysteries of space. To fully appreciate the impact of the Doppler effect, we must also consider the role of technology. In the field of medicine, the principles we have discussed come to life in the form of Doppler ultrasound. This technology utilizes sound waves to visualize blood flow within the body, revealing critical information about our health. As sound waves are directed towards moving blood cells, the frequency shifts based on their velocity. This allows healthcare professionals to assess circulation and detect potential issues, transforming the Doppler effect into a crucial diagnostic tool. The versatility of this phenomenon is a testament to its foundational importance in various fields. From the sounds of everyday life to the vastness of the cosmos, the Doppler effect connects us to the rhythm of the universe. It invites us to consider how sound shapes our understanding of the world, while simultaneously offering insights into the mysteries that lie beyond our reach. As we reflect on these concepts, let your mind wander to the many instances of sound and movement in your life. Each car horn, each train whistle, each heartbeat resonates with the principles we have explored. The Doppler effect is not merely a scientific curiosity, It is a reminder of the interconnectedness of our experiences, a thread that weaves through the fabric of reality. In this way, sound becomes a powerful storyteller, a medium through which we can explore the nuances of motion and perception. It invites us to listen deeply, to become attuned to the world around us, and to appreciate the beauty hidden within the waves that surround us. What stories lie within the sounds we encounter each day, and how do they shape our understanding of the universe? These questions linger in the air, waiting for answers, as we continue our journey through the fascinating world of sound. Chapter 4: Mathematical Foundation of the Doppler Effect. In the realm of sound and waves, the Doppler effect unfolds with an elegant mathematical foundation that allows us to understand the intricacies of frequency changes in relation to motion. At its core lies a formula that captures the relationship between the source of sound, the observer, and the medium through which the sound travels. This formula may seem complex at first glance, but it elegantly distills the essence of how movement alters our auditory experience. The Doppler effect formula can be expressed in a way that encapsulates three key variables: the speed of the sound source, the speed of the observer, and the medium itself. The beauty of this formula lies in its ability to quantify the shifts in frequency we perceive as the positions of the source and observer change. Imagine a symphony where the musicians are not static, but rather moving in relation to the audience. Just as the music transforms with their motion, so too does the sound we hear as our own position shifts in relation to the source. As we explore the variables, consider the speed of the source. When a sound-emitting object moves toward an observer, the sound waves compress, creating a higher frequency. Conversely, if the source moves away, the waves elongate, leading to a lower frequency. This is where the speed of the source plays its vital role, dictating how dramatically the frequency shifts. Now think about the observer's speed. If you were to move toward the sound source, you would encounter the waves more frequently than if you were stationary. This increased rate of wave encounters results in a higher perceived frequency. On the other hand, if you were to move away from the source, the opposite occurs and the frequency diminishes. The observer's speed acts as a catalyst that enhances or diminishes the auditory experience based on their movement relative to the source. Equally important is the medium through which sound travels. Sound waves require a medium, air, water, or solids to propagate. The speed of sound varies within these media. For example, sound travels faster in water than in air. Imagine standing at the edge of a serene lake, watching as ripples spread across the surface. The water allows sounds to travel swiftly, transforming a gentle splash into a clear melody that resonates through the environment. The properties of the medium not only influence the speed of sound, but also impact how we perceive the Doppler effect. Practical applications of the Doppler effect formula extend far beyond mere theory. In medicine, it plays a crucial role in ultrasound technology. By measuring the frequency shifts of sound waves reflected from moving objects within the body, healthcare professionals can assess blood flow and heart conditions. The Doppler effect serves as a powerful diagnostic tool, providing insights that would otherwise remain hidden beneath the surface. Imagine a doctor, equipped with an ultrasound device, guiding a small probe over a patient's abdomen. As sound waves travel through the body, they bounce off red blood cells in motion. The resulting frequency shifts reveal the speed and direction of blood flow, painting a vivid picture of the circulatory system. This application not only emphasizes the mathematical foundation of the Doppler effect, but also highlights its profound impact on human health. In astronomy, the Doppler effect finds its place among the stars. When we gaze into the night sky, we are not merely observing distant celestial bodies, we are witnessing the echoes of their movements. As stars and galaxies move toward or away from us, their light waves experience shifts in frequency, known as redshift and blueshift. This phenomenon provides astronomers with invaluable information about the universe's expansion and the motion of celestial objects. Consider the words of an esteemed astronomer who once stated that understanding the shifts in light from distant galaxies is akin to listening to the music of the cosmos. The Doppler effect allows us to perceive this cosmic symphony, revealing the rhythmic dance of celestial bodies as they traverse the vastness of space. In the realm of technology, the Doppler effect is harnessed in radar systems, which rely on the same principles to detect the speed of moving objects. Police radar guns measure the frequency change of radio waves bouncing off vehicles, providing accurate speed readings. This practical application brings the mathematical foundation of the Doppler effect into the everyday lives of many, illustrating how science intertwines with our daily routines. Think about the last time you were on the road, perhaps glancing at a police car with its radar gun. As the officer measures the speed of oncoming traffic, the Doppler effect is at play, capturing the essence of movement through mathematical calculation. This intersection of science and society showcases the profound ways in which the Doppler effect influences not just our understanding of waves, but also our interactions with the world around us. To further enrich our appreciation of the Doppler effect, it is essential to explore the implications of its mathematical foundation in our daily lives. Have you ever noticed how the sound of a passing train changes as it travels along the tracks? The Doppler effect encapsulates this experience, allowing us to perceive the world through the lens of motion and frequency. In essence, the Doppler effect invites us to listen more deeply to the symphony of our surroundings. As we encounter the sounds of life, from the gentle rustle of leaves to the distant echoes of thunder, we can appreciate the subtle shifts in frequency that accompany movement. This understanding fosters a connection between our experiences and the elegant mathematics that underpin them. As we journey through the intricacies of the Doppler effect, let us remember the words of a pioneering scientist who once remarked on the beauty of mathematics. It is the language with which the universe is written. Through the lens of this mathematical foundation, we gain clarity on how motion transforms sound, enriching our auditory experiences and deepening our understanding of the world around us. The Doppler effect is not merely a scientific concept. It is an invitation to listen closely, to observe the movement of life, and to marvel at the harmonious relationship between sound, motion, and the medium that carries it. As we continue to explore this captivating phenomenon, may we find solace in the knowledge that behind every sound we hear lies a complex interplay of mathematics and nature, waiting to be discovered. As we immerse ourselves in the mathematical foundation of the Doppler effect, it becomes essential to grasp the intricacies of the formula that governs this phenomenon. The heart of the equation lies in the interplay of the source speed, observer speed, and the medium through which the sound travels. Each variable contributes to the overall experience, shaping how we perceive the world around us. To visualize this, imagine a vibrant race, where sound waves are the runners racing alongside the source and observer. The speed of the source determines how quickly these waves are generated, while the speed of the observer dictates how frequently they arrive. The medium acts as the track, influencing the pace of the race itself. This dynamic interaction creates a beautiful symmetry, a harmonious convergence of mathematics and experience. The formula for the Doppler effect can be expressed in terms of these variables, allowing us to calculate the observed frequency based on the motion of the source and observer. For instance, when the source moves toward a stationary observer, the frequency increases, while the opposite occurs when the source moves away. This relationship is not merely theoretical. It has profound implications for our understanding of sound and motion. Consider how this mathematical foundation applies in practical scenarios. In weather forecasting, Doppler radar systems utilize the principles we are exploring to track storm systems and measure wind speeds. By analyzing the frequency changes of returned radar signals, meteorologists can detect the movement of precipitation and predict severe weather events. Picture the radar screen lighting up with colors, each hue representing different intensities and directions, shaping our understanding of the environment around us. In the realm of aviation, the Doppler effect plays a crucial role in navigation systems. Pilots rely on this phenomenon to gauge their speed relative to the ground, ensuring safe and efficient travel. As aircraft traverse the skies, they encounter varying wind conditions that can affect their speed. By utilizing the Doppler effect, pilots can make real-time adjustments, enhancing their flying experience and ensuring that they reach their destinations safely. Moreover, the implications of the Doppler effect extend into the field of acoustics. Sound engineers and musicians employ these principles to create immersive audio experiences. Imagine standing in a concert hall where the orchestra is positioned at different distances from the audience. As the musicians play, the intricacies of sound waves interact with the audience differently based on their proximity. The Doppler effect allows sound engineers to craft an auditory landscape that draws listeners into the performance, enveloping them in a rich tapestry of sound. The Doppler effect's applications in telecommunications are equally fascinating. In the world of wireless communication, the shifting frequencies of signals can impact the quality of our connections. Engineers harness the mathematical foundation of the Doppler effect to optimize satellite communications and improve the clarity of mobile calls. Picture a bustling city where conversations flow seamlessly through the air, each word transmitted with precision, thanks to the careful calibration of frequencies influenced by the Doppler effect. As we reflect on these practical applications, it becomes apparent that the mathematical underpinnings of the Doppler effect are woven into the very fabric of our daily lives. Each time we hear a siren in the distance or experience the changing pitch of a passing train, we engage with a complex interplay of variables that shape our auditory reality. Imagine yourself in a busy urban environment where the sounds of life ebb and flow around you. The chirps of birds, the hum of traffic, and the distant laughter of children create a vibrant soundscape. Each sound, each shift in frequency, speaks to the underlying mathematics at play. The Doppler effect invites us to listen more attentively, to discern the nuances that accompany movement and change. In contemplating the Doppler effect, we are reminded of the words of a visionary in the field of physics, who expressed the importance of understanding natural phenomena. If you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. This quote resonates profoundly as we explore how the Doppler effect encapsulates the essence of motion, frequency, and our perception of sound. As we continue to delve into this captivating subject, let us remain open to the wonders that the Doppler effect reveals. It is not merely a scientific principle. It is a lens through which we can appreciate the intricate relationships between sound, movement, and the world around us. Each time we experience the world through sound, we are engaging with a profound mathematical truth that enriches our lives in ways we may not even realize. In our exploration of the Doppler effect, we uncover a deeper understanding of the universe, a universe where sound, motion, and mathematics converge in a beautiful symphony. By embracing this knowledge, we cultivate a greater appreciation for the sounds that envelop us, recognizing the intricate dance of waves that shape our auditory experiences. As we move forward, let us carry this understanding with us, allowing the Doppler effect to illuminate our perceptions and deepen our connection to the world we inhabit. The mathematical foundation of this phenomenon serves not only as a scientific tool, but also as a reminder of the beauty found in the intricate patterns of nature. Each sound we hear is a whisper of the universe, inviting us to listen closely and marvel at the symphony of life around us. Chapter 5: Applications in Astronomy and Space Science. The vastness of space holds secrets that have intrigued humanity for centuries, and at the heart of many of these revelations lies the Doppler effect. This phenomenon, which we have explored in relation to sound waves, finds profound applications in the realm of astronomy. Imagine standing under a starry sky, the twinkling lights above serving as a reminder of the countless stars, planets, and galaxies that populate our universe. How do we come to understand the movement of these celestial bodies? The answer lies in observing the changes in light that reach us from distant stars. When we speak of measuring star velocities, we are tapping into the very essence of the Doppler effect. Just as sound waves shift in frequency depending on the motion of their source, light waves do the same. When a star moves toward Earth, the wavelengths of light it emits become compressed, resulting in a phenomenon known as blue shift. Conversely, when a star moves away, the wavelengths stretch, leading to redshift. Picture this: as a train whistle changes pitch when it speeds past, so too does the light from a star morph according to its movement. This shift allows astronomers to measure how fast stars are traveling through the cosmos. You can visualize this concept by imagining the sound of an approaching train. The closer it gets, the higher the pitch you hear, and as it passes, the sound drops to a lower tone. This same auditory experience translates beautifully into the realm of light. When we observe the light from a star, blue shift indicates it is racing towards us, while redshift tells us it is receding into the depths of space. Now, why is this important? Understanding the velocities of stars and galaxies provides insights into their interactions and the dynamics of our universe. As we delve deeper into these cosmic measurements, we begin to grasp a larger narrative: the expanding universe. The implications are profound, suggesting that everything we see around us is part of a vast, dynamic system that is continually evolving. The concept of an expanding universe was first championed by the Belgian priest and astronomer Georges Lemaitre, who theorized that the universe began from a singular point, a primeval atom, and has been expanding ever since. This idea was later solidified through observations of redshift, especially by Edwin Hubble, whose work demonstrated that distant galaxies are moving away from us. Imagine taking a moment to ponder the enormity of this claim. The universe is not static, but is instead a living entity, stretching and growing, with galaxies drifting farther apart over time. As we consider Hubble's observations, it's fascinating to think about the implications of redshift. When we observe that a galaxy's light is redshifted, we are witnessing a cosmic ballet of motion that reveals the very fabric of space-time. Every redshift measurement tells us a story about the history of that galaxy, its velocity, and how it fits into the larger structure of the universe. Each star, each galaxy, is a participant in this intricate performance, moving through the vast expanse of space. The relationship between redshift and the expanding universe opens the door to even more profound questions. What does this mean for our understanding of the cosmos? If galaxies are racing away from us, what does that imply about the origins of the universe and its ultimate fate? The answers to these questions continue to elude us, yet they drive scientists and astronomers to explore further, to push the boundaries of our knowledge. Imagine gazing at the night sky, filled with stars and galaxies. Each pinprick of light is not just a visual spectacle but a messenger from the past. The light we see today left its source millions, or even billions, of years ago. This means that when we look at a distant star, we are not only seeing its present state, but also its history. The redshift of its light allows us to understand not just its velocity, but also its journey through time and space. As we reflect on the role of the Doppler effect in astronomy, we realize that it is a lens through which we can explore the universe. It is a tool that enables us to measure the unmeasurable, to grasp the unfathomable. The Doppler effect does not merely provide data. It enriches our narrative about the universe, transforming abstract concepts into tangible understanding. In the context of the expanding universe, the Doppler effect invites us to ponder the very nature of existence. Are we alone in this vast expanse? What other worlds may be out there, with their own stories waiting to be told? The light we observe, shifting between red and blue, connects us to a shared cosmic heritage. As we consider the implications of redshift and blueshift, we start to weave together the threads of our understanding. These shifts are not just scientific measurements, they are the heartbeat of the universe, resonating through the cosmos. Each star, each galaxy, contributes to an ever-evolving narrative that reflects the dance of creation and destruction, of birth and death on a cosmic scale. The Doppler effect, once an observation of sound, has become a bridge to understanding the universe's vastness. It leads us to ask not only how fast stars are moving, but also what they reveal about the very fabric of reality itself. Imagine the excitement of scientists, peering through telescopes, measuring the light from distant galaxies, and realizing they are witnesses to the universe's unfolding story. As we continue to explore these cosmic phenomena, we gain insight into the forces that shape our universe. The Doppler effect is a reminder of the interconnectedness of all things. The rhythms of the universe echo the principles of sound, revealing that at a fundamental level, the same forces govern the behavior of waves, whether they be in the air, in the ocean, or in the fabric of space-time itself. The quest for knowledge in astronomy is a journey without end, each discovery leading to new questions and deeper mysteries. The Doppler effect serves as a guiding principle, illuminating the pathways we traverse as we seek to understand our place in the cosmos. As we look to the stars, we are compelled to dream, to wonder, and to explore the infinite possibilities that lie beyond the horizon of our current understanding. The exploration of redshift and blueshift not only sheds light on the movement of stars and galaxies, but also reveals the underlying structure of the universe. These shifts in light serve as cosmic markers, guiding astronomers and physicists in their quest to map the vast expanse of space. When we observe the light from distant celestial bodies, the redshift indicates that these objects are receding, while blueshift suggests they are approaching. This simple yet profound observation has led to the realization that the universe is not static. It is a dynamic, ever-evolving entity. Imagine gazing into the night sky, where each point of light represents a world of its own, with stories etched in the wavelengths of light that travel across the cosmos. The concept of redshift can be likened to a cosmic signal, a whisper from the past that tells us about the universe's expansion. As light travels through the vacuum of space, it encounters the influence of gravity and the fabric of spacetime itself, which stretches and pulls on the waves of light emitted by distant galaxies. This interaction leads to a change in frequency, allowing us to interpret the history and movement of these celestial entities. The implications of these observations are profound. They open a window into our understanding of the universe's expansion, a concept initially posited through the pioneering work of Edwin Hubble. Hubble's observations provided the first clear evidence that galaxies were moving away from us, a realization that transformed our comprehension of the cosmos. Reflect on this. If we can measure how fast a galaxy is receding based on its redshift, what other secrets might the light from these galaxies hold? Each measurement is a piece of a grand puzzle, revealing the intricate dance of the universe's expansion. In contemplating the significance of redshift, we find ourselves standing on the shoulders of giants. Hubble's law, which describes the relationship between a galaxy's distance and its velocity, has become a cornerstone of modern cosmology. It suggests that the farther away a galaxy is, the faster it is moving away from us. This observation leads us to question the very nature of our universe. Could it be that all galaxies originated from a singular event, a cosmic birth that set everything into motion? As we dive deeper into the implications of an expanding universe, we cannot ignore the role of dark energy, a mysterious force that drives this expansion. Imagine a fabric stretching infinitely, yet being tugged by an unseen force, causing it to expand at an accelerating rate. Dark energy composes a significant portion of the universe, yet its true nature remains elusive. This prompts us to ponder. If dark energy is pushing galaxies apart, what does that mean for the future of our universe? To visualize these concepts, picture a balloon being inflated. As the balloon expands, the dots drawn on its surface move farther apart from one another. This analogy captures the essence of the universe's expansion. The galaxies, like the dots on the balloon, are not just drifting through empty space. They are part of a grand design that continues to evolve. With each passing moment, we are reminded of the delicate balance between forces that govern the cosmos. In the realm of astronomy, the measurements derived from redshift and blueshift are pivotal. They enable scientists to map the universe's structure, identify galaxy clusters, and even infer the presence of unseen matter. By understanding how light behaves as it travels through the cosmos, we gain insights into the distribution of galaxies and the cosmic web that connects them. Imagine this web as the intricate lattice of a spider's silk, with galaxies serving as nodes in a vast network, all interconnected through the fabric of space-time. As we reflect on the contributions of astronomers and physicists, we recognize the collaborative nature of scientific discovery. Each breakthrough builds upon the work of those who came before, forming a lineage of knowledge that transcends generations. This unity of purpose, driven by curiosity and wonder, fuels the journey into the unknown. As we look at the stars, we are not just observers, we are participants in a shared exploration of existence. The Doppler effect provides the framework through which we can interpret these cosmic signals, turning the light emitted by stars into a language we can understand. The shifts between red and blue serve as a reminder of the vast distances and timescales involved, as well as the intricate interactions that occur across the universe. Each observation is an invitation to delve deeper, to ask questions, and to seek answers that may redefine our understanding of reality. As we consider the future of astronomy, we find ourselves on the brink of new discoveries. With advancements in technology, telescopes are now capable of peering further into the universe than ever before. Imagine the excitement of uncovering new galaxies, hidden behind the veil of time, their light finally reaching us after eons of travel. Each new discovery adds to our understanding of the cosmos, creating a richer narrative about the universe's past and its potential future. The exploration of the universe is not merely an academic pursuit, it is a deeply human endeavor. We seek to understand our origins, our place in the cosmos, and the forces that shape our existence. The Doppler effect, with its profound implications for measuring star velocities and the expansion of the universe, serves as a bridge between the known and the unknown. It encourages us to dream, to question, and to pursue knowledge with relentless curiosity. As we continue to examine the applications of the Doppler effect in astronomy and space science, we find ourselves engaged in an ever-evolving dialogue with the cosmos. The stars above are not just distant objects, they are storytellers, offering glimpses into the past and hints about the future. Each shift in light, each measurement of velocity, is a reminder of the interconnectedness of all things and the beauty of discovery that awaits us. Chapter 6: Doppler Effect in Medical Imaging Technologies. The Doppler effect extends its influence beyond the realm of sound and light, finding a vital role in the field of medical imaging technologies. Among the most significant applications is Doppler ultrasound, a technique that has revolutionized how healthcare professionals assess blood flow within the body. Imagine a serene medical environment where the quiet hum of equipment accompanies the soft beeping of monitors. In this space, the Doppler ultrasound machine stands as a bridge between the unseen world of blood circulation and the keen observation of healthcare practitioners. Doppler ultrasound harnesses the principles of the Doppler effect to visualize blood flow. As sound waves are emitted into the body, they encounter moving red blood cells. When these cells move toward the ultrasound probe, the frequency of the sound waves increases, creating a higher pitch. Conversely, as the blood cells move away, the frequency decreases, resulting in a lower pitch. This change in frequency allows clinicians to determine not just the presence of blood flow, but also its speed and direction. Picture a flowing river, where the current can be swift in some areas and gentle in others. The Doppler ultrasound provides a map of this internal river, offering insights into the dynamics of circulation that are critical for patient care. One of the most profound applications of Doppler ultrasound is in obstetrics. Expectant parents can hear their baby's heartbeat for the first time, a moment filled with joy and anticipation. The ability to monitor fetal heart rate through Doppler technology serves as a vital indicator of the baby's well-being. By tracking the blood flow in the umbilical cord and assessing the heart's rhythm, healthcare providers can ensure that the developing fetus is thriving. This remarkable ability to listen to life as it unfolds has created an emotional connection for families, transforming a clinical procedure into a deeply personal experience. In addition to obstetrics, Doppler ultrasound plays a crucial role in cardiology. Consider the heart, a powerful muscle that tirelessly pumps blood throughout the body. Through Doppler imaging, physicians can visualize blood flow across heart valves and within chambers, identifying abnormalities that may indicate conditions such as valvular heart disease or congenital heart defects. By understanding the flow dynamics, doctors can make informed decisions about treatment options, potentially saving lives. This technology exemplifies how scientific advancements weave into the fabric of healthcare, providing tools that enhance diagnostic accuracy and patient outcomes. Yet, like any technology, Doppler imaging comes with its own set of benefits and limitations. Among the many advantages, its non-invasive nature stands out. Patients can receive essential diagnostic information without the need for surgical procedures or exposure to radiation. This aspect alone makes Doppler ultrasound a preferred choice for many clinicians, particularly when monitoring vulnerable populations such as pregnant women and children. The convenience and safety of this method open doors for routine assessments that aid in early detection and intervention. However, it is essential to acknowledge the limitations inherent in Doppler imaging techniques. While they provide invaluable information about blood flow, they are not without challenges. For instance, the accuracy of measurements can be affected by factors such as the angle of inclination, the position of the probe, and the presence of intervening tissues. Imagine trying to listen to a soft melody through a thick wall. the sound would be muffled and distorted. Similarly, when sound waves encounter obstacles, they can scatter, making it difficult to obtain precise readings. Clinicians must navigate these challenges with skill and experience, often supplementing Doppler ultrasound with other imaging modalities to achieve a comprehensive understanding of a patient's condition. As we explore the nuances of Doppler ultrasound, it is fascinating to consider how far we have come since its inception. The journey of this technology is marked by the contributions of countless individuals who have dedicated their lives to advancing medical imaging. Among them is Dr. Thomas M. Burchill, a pioneer in the field of Doppler ultrasound, who articulated the profound impact of this technology by stating that it allows us to see the unseen. His words resonate deeply within the medical community, emphasizing the transformative power of visualization in diagnosing and treating diseases. Imagine the world of medical imaging as a vast landscape where each technique offers unique insights. Doppler ultrasound occupies a special place within this landscape, bridging the gap between sound and sight. It is a reminder of how the principles we have studied in the context of sound waves are intricately woven into the fabric of healthcare. The Doppler effect, which we have come to understand as a phenomenon of frequency change, now serves as a vital tool for assessing the health of individuals, contributing to the ongoing narrative of medical progress. In this ongoing exploration, we find ourselves pondering the future of Doppler imaging technologies. As advancements in technology continue to evolve, the potential for enhanced precision and new applications becomes increasingly apparent. Imagine a future where artificial intelligence can assist in interpreting Doppler images, providing real-time analysis that empowers clinicians to make swift, informed decisions. The possibilities are as expansive as the human imagination, hinting at a landscape where healthcare is continuously redefined. Through the lens of the Doppler effect, we can appreciate not only its scientific underpinnings, but also its profound implications for human health. Each heartbeat, each pulse of blood flowing through our veins, represents a story waiting to be told. Doppler ultrasound allows us to listen to these stories, translating the silent rhythms of life into a language we can understand. As we continue to navigate this fascinating terrain, we find ourselves connected to the intricate web of life that surrounds us, a reminder of the delicate balance that sustains our existence. As we immerse ourselves in the world of Doppler ultrasound, we uncover a wealth of information about how blood flow is assessed, particularly in instances where precision is paramount. This technology transcends mere imaging. It offers a real-time glimpse into the circulatory system, enabling clinicians to detect anomalies that might otherwise remain hidden. The evaluation of blood flow is crucial in diverse medical scenarios, ranging from diagnosing cardiovascular conditions to monitoring the health of fetuses in utero. In essence, Doppler ultrasound serves as a conduit through which we can visualize the dynamics of blood circulation. When sound waves are transmitted into the body, they interact with moving blood cells, producing a frequency shift that can be quantified and interpreted. Imagine a serene pond where the gentle ripples represent blood flow. As you toss a pebble into the water, the ripples move outward, creating patterns that reflect the underlying currents. Similarly, the Doppler effect captures the behavior of blood as it courses through arteries and veins, revealing the variations in velocity and direction. The assessment of blood flow using Doppler ultrasound can take various forms, each tailored to specific clinical needs. One common method is color Doppler imaging, where color is superimposed on traditional grayscale images to depict the direction and velocity of blood flow. This technique provides a vivid representation, making it easier for healthcare providers to identify abnormalities such as blockages or turbulent flow. It's akin to watching a colorful painting come to life, where the colors express the rhythm of life coursing through our veins. In addition to color Doppler, spectral Doppler is another powerful modality that quantifies blood flow in a more detailed manner. It captures the velocity of blood at specific points, presenting this information on a graph that displays the relationship between time and speed. Picture a calm river with a speedometer measuring the current at various points along its banks. Just as this speedometer provides insights into the river's flow dynamics, spectral Doppler offers clinicians critical data that can be vital for diagnosing conditions like deep vein thrombosis or assessing the severity of valvular heart disease. Yet, as we embrace the advantages of Doppler imaging, we must also consider the limitations that accompany these techniques. One significant challenge is the reliance on operator skill and experience. The effectiveness of Doppler ultrasound depends heavily on the clinician's ability to position the probe correctly, interpret the results accurately, and account for anatomical variations. Imagine a skilled painter who, with each brushstroke, transforms a blank canvas into a vivid masterpiece. Similarly, a proficient technician can unlock the potential of Doppler ultrasound, translating complex flow patterns into meaningful clinical insights. Moreover, the quality of the images obtained can be affected by patient factors, such as body habitus and tissue composition. In some cases, excessive body fat or the presence of gas in the gastrointestinal tract can hinder the transmission of sound waves, leading to suboptimal imaging. In these instances, clinicians may need to employ alternative imaging modalities, such as magnetic resonance imaging or computed tomography, to obtain a complete picture of the patient's condition. This necessity for complementary techniques highlights the importance of a comprehensive approach to diagnosis, one that embraces the strengths of various imaging technologies. As we reflect on the journey of Doppler ultrasound, we also recognize the contributions of those who have shaped this field. Influential figures, such as Dr. Carl Dusek, who pioneered the use of ultrasound in medical diagnostics, laid the groundwork for the transformative applications we see today. His vision and determination have inspired generations of researchers and clinicians, driving innovation and expanding the horizons of medical imaging. With the ever-evolving landscape of medical technology, the future of Doppler imaging promises even greater advancements. Imagine a world where enhanced algorithms and artificial intelligence analyze blood flow data in real time, providing instant feedback to healthcare professionals. This synergy between human expertise and machine learning could lead to more accurate diagnoses and tailored treatment plans, revolutionizing patient care. The prospect of integrated imaging systems that combine Doppler ultrasound with other modalities is equally exciting, offering a comprehensive understanding of cardiovascular health. As we navigate this fascinating intersection of technology and medicine, it is essential to remain mindful of the human element that underpins patient care. The Doppler effect, while rooted in scientific principles, also serves as a reminder of the stories that lie within each patient. The rhythms of their heartbeats and the currents of their blood flow are not just data points. They embody the essence of life itself. Doppler ultrasound allows us to listen to these stories, translating the silent whispers of biology into a language that can inform and guide clinical decisions. Thus, in the realm of medical imaging, the Doppler effect stands as a testament to the profound connections that exist between science and humanity. Each pulse of sound waves carries with it the potential to unveil mysteries, illuminate paths to healing, and foster a deeper understanding of the intricate systems that sustain life. As we continue to explore the depths of this technology, we find not only advancements in diagnostics, but also a reaffirmation of our shared experience as human beings navigating the complexities of health and wellness. Chapter 7: Radar and the Doppler Effect in Technology. Radar technology is a fascinating realm where the principles of wave behavior converge with practical applications, transforming how we perceive and interact with the world around us. At its core, radar, which stands for radio detection and ranging, operates by emitting radio waves and analyzing the echoes that bounce back from objects. Picture a serene landscape, where an unseen pulse of energy travels through the air, seeking out and revealing hidden forms. This method of exploration allows us to detect the presence, distance, and even speed of various objects, whether they be aircraft soaring high above or weather systems gathering on the horizon. The functionality of radar systems is rooted in the fundamental principles of wave propagation. When the radar emits radio waves, these waves travel through the atmosphere until they encounter an object. Upon striking this object, the waves are reflected back to the radar receiver. By calculating the time it takes for the waves to return, the radar system can determine how far away the object is located. Imagine standing on a dock, tossing a stone into a still lake. The ripples spread outwards until they strike the distant shore, returning to greet you moments later. Just as those ripples carry information about the shoreline, radar waves relay critical data about the objects they encounter. Radar technology has evolved significantly since its inception in the early 20th century. One of the key figures in its development was Sir Robert Watson-Watt, who pioneered the use of radar during World War II. His innovative work not only changed the course of the war, but also laid the foundation for modern radar applications. Today, radar systems are utilized in various fields, including aviation, meteorology, and law enforcement, showcasing their versatility and adaptability. In weather forecasting, the application of the Doppler effect enhances the capabilities of radar systems, providing a deeper understanding of atmospheric phenomena. Doppler radar, in particular, is instrumental in tracking precipitation and analyzing wind patterns. Imagine a vast, rolling storm cloud, pregnant with rain, as it approaches your vicinity. The radar waves penetrate the cloud, encountering raindrops and other particles. Just as we have learned about the changes in sound waves, the Doppler effect applies here, altering the frequency of the returning waves based on the motion of the raindrops relative to the radar. As the storm clouds move, the Doppler radar detects these shifts in frequency, allowing meteorologists to determine not only the location of the precipitation, but also its speed and direction. This vital information empowers weather forecasters to provide timely warnings about severe weather events, such as thunderstorms or tornadoes. Imagine the comfort of knowing that, thanks to this technology, you are informed about the impending storm, giving you the chance to seek shelter or prepare accordingly. The use of Doppler radar extends beyond weather forecasting into the realm of law enforcement, where it plays a vital role in speed detection. Picture a quiet stretch of road where vehicles glide smoothly along the asphalt. Law enforcement officers utilize radar guns equipped with Doppler technology to monitor the speed of these vehicles. When a car approaches, the radar gun emits a signal which reflects off the moving vehicle. As the car travels toward the officer, the frequency of the reflected waves increases, providing an accurate measurement of its speed. Conversely, as the vehicle moves away, the frequency decreases. This application of the Doppler effect has proven invaluable in maintaining public safety on the roads. It serves not just as a tool for enforcement, but also as a deterrent, reminding drivers of the importance of adhering to speed limits. The implications of this technology extend further, as it fosters a culture of awareness and responsibility among motorists. Consider the contributions of notable individuals in this field, such as Dr. Robert H. Goddard, a pioneer of rocket propulsion who understood the significance of wave dynamics in space exploration. Goddard's insights into the behavior of waves have influenced various technologies, including radar systems that are now used to monitor air traffic and ensure the safety of millions of passengers every day. His work exemplifies the interconnectedness of different scientific disciplines and how advancements in one area can lead to breakthroughs in another. As we explore the depths of radar technology and the Doppler effect, we uncover a world where science and innovation weave together seamlessly. Each pulse of a radar wave carries with it the potential to unveil hidden truths, whether they lie within the clouds above or the vehicles that traverse our roads. Imagine the vast network of radar systems working harmoniously, each contributing to a collective understanding of our environment. In the realm of meteorology, Doppler radar has transformed the landscape of weather forecasting. The ability to visualize storm systems in real time allows forecasters to provide accurate and timely updates, ensuring that communities are prepared for impending weather changes. This advancement is particularly crucial in regions prone to severe storms, where every minute counts. The integration of technology and natural science exemplifies the beauty of human ingenuity. As we stand on the precipice of discovery, we are reminded that the innovations of today are built upon the foundations laid by those who came before us. Each advancement in radar technology contributes to a more connected and informed society, where knowledge empowers individuals to make better decisions. How does this interplay of waves, motion, and technology shape our understanding of the world? It invites us to consider the unseen forces at play, connecting us to the broader universe. The Doppler effect, with its rhythmic shifts in frequency, illustrates the dynamic nature of our surroundings and the intricate dance of energy that permeates our existence. Envision a future where radar technology continues to evolve, perhaps integrating with artificial intelligence to enhance its capabilities. Such advancements may lead to even more precise weather predictions, safer roads, and improved public safety. The potential is boundless, and it is rooted in the principles we explore today. As we reflect on the journey of radar and the Doppler effect, we gain appreciation for the multitude of applications that arise from these concepts. They not only enhance our understanding of the physical world, but also serve as a testament to humanity's quest for knowledge and improvement. Consider how these technologies have touched everyday lives, from the moment a weather alert pings on a smartphone to the quiet assurance of knowing that speed limits are monitored, contributing to safer highways. Each interaction with these systems is a reminder of the unseen waves that surround us, guiding and protecting us in various ways. The Doppler effect, in its many forms, continues to inspire innovation across different fields. It challenges us to look beyond the surface, to seek understanding in the waves of sound, light, and movement that define our experiences. As we delve deeper into the realms of technology and science, we discover that the connections we forge today will shape the future we inhabit tomorrow. In this intricate interplay of technology and nature, the possibilities are as expansive as the dark night sky, filled with twinkling stars that have traveled light years to reach our gaze. Each star, each wave, each pulse of energy tells a story, a narrative that resonates through time and space. The journey of radar and the Doppler effect is but one chapter in this grand narrative, inviting us to explore further and uncover the mysteries that await. As we immerse ourselves further into the world of radar technology and the Doppler effect, we begin to appreciate the intricate relationship between science and everyday life. The applications of these principles are not only fascinating, but also essential as they enhance our ability to monitor and respond to various phenomena. In the domain of weather forecasting, Doppler radar stands out as a transformative tool that enables meteorologists to visualize atmospheric conditions in real time. Imagine a vast network of radar systems, each pulsating with energy, scanning the skies for signs of weather changes. This technology allows forecasters to track storm systems with remarkable precision, offering insights that were once mere guesses based on observational data alone. The Doppler effect plays a critical role in this process. As the radar waves encounter moving precipitation, they reveal not just the location of rain or snow, but also how fast these elements are moving and in which direction. Picture a heavy rainstorm sweeping across a landscape, the radar illuminating its path. The Doppler radar detects changes in the frequency of returning waves, allowing meteorologists to identify areas where the storm is intensifying or weakening. This capability is particularly crucial during severe weather events, such as hurricanes and tornadoes. Imagine the urgency felt by forecasters as they analyze the data, striving to provide timely warnings to communities at risk. The ability to present accurate information can mean the difference between safety and disaster. It is a testament to how science, through the lens of technology, can save lives and mitigate the impacts of natural calamities. The application of radar technology extends into the realm of law enforcement, where it serves as a vital instrument for ensuring public safety. With the integration of Doppler radar in speed detection systems, officers are equipped with precise tools to monitor vehicle speeds on roadways. Envision a tranquil highway, where the flow of traffic is punctuated by the occasional rush of a speeding vehicle. Law enforcement officers utilize radar devices to capture the speed of these vehicles, all while remaining discreetly stationed. As a car approaches, the radar device emits a signal that bounces back upon contact with the vehicle. The change in frequency of the returning waves allows the officer to determine the vehicle's speed instantly. It's a harmonious blend of technology and law enforcement, where the Doppler effect becomes a guardian of the roads, helping to maintain order and safety. This practice not only enforces speed limits, but also serves as an educational tool for drivers. Consider how each radar reading serves as a reminder of the responsibilities that come with operating a vehicle. The presence of radar technology encourages drivers to remain vigilant and respectful of speed limits, fostering a culture of safety. Beyond its immediate applications, the advancements in radar technology and the understanding of the Doppler effect are paving the way for future innovations. Imagine a world where radar systems are further enhanced with artificial intelligence, capable of processing vast amounts of data in real time. Such developments could lead to even more accurate forecasting, allowing communities to prepare for weather changes with unprecedented precision. Moreover, the integration of radar systems into smart city designs holds great promise. Imagine urban landscapes where traffic flow is continually monitored and adjusted through the synchronization of radar data and traffic signals. This could minimize congestion and reduce the likelihood of accidents, showcasing how technology can foster a more harmonious coexistence among urban dwellers. The contributions of scientists and innovators throughout history have brought us to this point where radar technology is a cornerstone of various fields. We can draw inspiration from pioneers who recognize the significance of wave behavior, such as Albert Michelson, known for his work in measuring the speed of light. Michelson's meticulous experiments provided a deeper understanding of wave dynamics, laying the groundwork for future advancements in radar systems and beyond. As we reflect on the impact of radar and the Doppler effect, we are reminded of the interconnectedness of these scientific principles with our daily lives. Each pulse of a radar wave is a reminder of the complexities of the world around us, revealing insights that often go unnoticed. In the vast tapestry of life, we find that these technologies, while rooted in scientific principles, ultimately serve a greater purpose, connecting us, protecting us, and enhancing our understanding of the environment we inhabit. Imagine how different our lives would be without these advancements, how much less informed we would be about the natural world and how it interacts with our human activities. Through the lens of radar and the Doppler effect, we glimpse the beauty of scientific inquiry. Each discovery leads to new questions and possibilities, inspiring future generations to explore and innovate. As we embrace these technologies, we step into a future where knowledge and understanding continue to flourish, creating a safer, more informed world for all. Chapter 8: Challenges and Limitations of the Doppler Effect. As we consider the Doppler effect, it is essential to acknowledge the factors that can impact the accuracy of its measurements. While this phenomenon offers profound insights into sound and light, the environment in which these measurements are taken can greatly influence the results. Imagine standing in a quiet, open field where the sound of a distant train can be heard clearly. Now, contrast that with the experience of trying to discern the same sound in a bustling city, filled with the cacophony of honking horns, chattering pedestrians, and the constant hum of machinery. In the latter scenario, the clarity of the Doppler effect becomes obscured, making it challenging to accurately perceive the nuances of frequency changes. Environmental noise introduces a layer of complexity. When sound waves intermingle with other waves in a noisy setting, the clarity of the original signal is diminished. The Doppler effect relies on the precise detection of frequency shifts to provide accurate readings. Any interference can lead to miscalculations. Picture a calm pond disturbed by a sudden gust of wind. The ripples become chaotic, obscuring the stillness that once existed. In the world of sound, this chaos can make it nearly impossible to discern the subtle shifts that signify movement. In addition to noise, extreme conditions can also pose challenges. Consider a scenario where sound must travel through varying temperatures or mediums, such as water or dense fog. Each of these conditions can alter the speed of sound, complicating the calculations needed to interpret Doppler measurements accurately. In colder air, sound travels slower, while in warmer conditions, it speeds up. This variability means that an observer must account for these changes if they are to make precise assessments. The Doppler effect may be a reliable tool, but it is not infallible. One notable example of the challenges posed by extreme conditions can be found in the field of astronomy. Astronomers often rely on the Doppler effect to study the movement of stars and galaxies. However, when observing celestial bodies through Earth's atmosphere, the effects of turbulence and distortion can lead to inaccuracies. Imagine gazing at the stars on a clear night, only to find them shimmering like a mirage. This phenomenon occurs due to atmospheric disturbances, which can scatter light and affect the wavelengths that reach our telescopes. As a result, the interpretation of redshift and blueshift can be skewed, complicating our understanding of the universe's expansion. Public discourse around the Doppler effect can often lead to misinterpretations that cloud its scientific significance. The allure of this phenomenon, coupled with its applications in various fields, has led to oversimplified explanations that can mislead the general public. For instance, when discussing the Doppler effect in relation to sound, one might hear the phrase, "the sound gets louder as it approaches." While this captures part of the experience, it neglects the subtleties of how frequency and pitch interact. Imagine a child describing the sound of a passing ambulance. They might say, "It gets louder." However, this description only hints at a deeper truth. The pitch rises as the vehicle approaches, a phenomenon that occurs due to the compression of sound waves. Simplifying these concepts can lead to misunderstandings about how sound and motion interact, as well as the underlying physics that govern these changes. Moreover, the popularity of the Doppler effect in popular culture can sometimes overshadow its scientific principles. People may reference it in discussions about speed or movement without grasping its true intricacies. For example, when a sports commentator describes a moving vehicle in terms of the Doppler effect, they might focus on the sound alone, overlooking the broader implications of this shift in frequency. Such moments can create an image of the Doppler effect as merely a curiosity rather than a powerful tool for understanding the world. In the realm of medical imaging, where the Doppler effect is employed to assess blood flow, public understanding can also falter. The use of Doppler ultrasound has revolutionized how healthcare professionals visualize blood circulation, yet misconceptions about its functionality can lead to confusion. Patients may hear the term Doppler and associate it solely with the sound of the device rather than the complex science behind it. The soothing sound waves emitted by the ultrasound might be interpreted as merely a diagnostic noise rather than the result of intricate frequency analysis. As we delve into the role of the Doppler effect in technology, it becomes clear that accuracy is paramount. In fields such as radar and sonar, the clarity of measurements can be compromised by environmental factors, as previously discussed. Imagine a radar system trying to track a fast-moving object amidst a thunderstorm. The heavy rain and wind can scatter radio waves, leading to inaccuracies in speed and distance calculations. These challenges highlight the importance of understanding the limits of the Doppler effect in practical applications. The interplay between sound, light, and motion is a delicate one, and the nuances of the Doppler effect require careful consideration. As we explore the vast expanse of knowledge that surrounds this phenomenon, it is essential to remain grounded in its scientific principles while appreciating the beauty of its applications. Each measurement, each frequency shift, and each observation contributes to a broader understanding of our world, yet they are not without their challenges. The Doppler effect, while a remarkable tool, is not immune to the complexities of the environment and human interpretation. As we continue to explore its vast implications, we must remain mindful of the limitations that can arise and strive for clarity in our understanding. The wonder of this phenomenon lies not only in its applications, but also in the intricate dance of science and perception that shapes our experience of the universe. As we deepen our exploration of the Doppler effect, we encounter further challenges that can obscure the precision of this phenomenon. One such challenge arises from the inherent limitations of measurements taken in noisy environments or extreme conditions. The world around us is an orchestra of sounds, and amidst this symphony, the delicate shifts in frequency that the Doppler effect reveals can easily be drowned out. Imagine standing at the edge of a bustling city during rush hour. The blare of horns, the chatter of pedestrians, and the distant rumble of construction fill the air. In this chaos, how can one discern the subtle shifts in the pitch of an approaching emergency vehicle? The background noise plays a significant role in masking the very essence of the Doppler effect. This interference can lead to misinterpretations. where the observer might perceive the sound as louder or softer without fully grasping the intricate dance of frequency changes. In addition to urban noise, consider extreme weather conditions, such as heavy rain or strong winds. These atmospheric disturbances can distort sound waves, altering their speed and complicating the calculations necessary for accurate Doppler measurements. Just as a gentle breeze can carry the sound of rustling leaves, a storm can scatter those very waves, creating a barrier to clarity. In the realm of radar technology, similar challenges emerge. Radar systems rely on the detection of reflected waves to ascertain the speed and distance of objects. However, when these waves encounter turbulent weather, their efficacy is compromised. Imagine a radar operator attempting to track a fast-moving storm system. The heavy precipitation and turbulent air can scatter the radio waves, leading to inaccuracies that could have significant consequences in navigation and safety. Public discourse often amplifies these challenges, as the complexities of the Doppler effect can be lost in translation. Misinterpretations abound, especially when individuals attempt to simplify scientific concepts for broader audiences. For instance, when discussing the Doppler effect in everyday terms, people might say that sound gets higher as it approaches. While this statement captures a fragment of the truth, it overlooks the more profound implications of frequency shifts. Consider how a child might describe the sound of a passing train. They may excitedly exclaim, "It gets louder." This perspective, while capturing the excitement of the moment, fails to convey the underlying mechanics of how sound waves compress and expand. By reducing complex science to simplistic phrases, we risk diminishing the understanding of the Doppler effect's significance in various fields. Moreover, the portrayal of the Doppler effect in media and popular culture can contribute to misconceptions. The frequent references to this phenomenon in movies, television shows, and even sports commentary often focus on the auditory aspects rather than the underlying physics. For instance, a sports commentator might mention the Doppler effect while describing a speeding car, yet they may neglect to explain how the sound waves change as the vehicle approaches and recedes. This oversimplification can lead to an impression that the Doppler effect is merely a curiosity, rather than a powerful scientific tool that enhances our comprehension of motion and velocity. In the medical field, where the Doppler effect plays a crucial role in diagnosing and monitoring blood flow, patient understanding can also be clouded by simplifications. Doppler ultrasound technology provides a vital window into the circulatory system, allowing clinicians to visualize blood flow and detect abnormalities. Yet, when patients encounter the term Doppler, they may associate it solely with an auditory experience rather than appreciating the complex interplay of sound waves and blood movement. The soothing beeps and hums of the ultrasound machine can appear as mere background noise, masking the intricate science that enables healthcare providers to perform life-saving assessments. As we consider the implications of the Doppler effect in our daily lives, we must remain vigilant about the limitations that can arise from environmental factors and public interpretation. The world is a rich tapestry of sound and light, yet the clarity of our understanding can often be obscured by the very conditions that allow us to experience it. Reflecting on the experiences of notable figures in science can illuminate the importance of clear communication and understanding. Scientists like Albert Einstein, who famously remarked that, "If you can't explain it simply, you don't understand it well enough," remind us of the need to bridge the gap between complex theories and public comprehension. The Doppler effect, while a fascinating and multifaceted phenomenon, requires careful articulation to ensure that its significance is not lost in oversimplifications or misunderstandings. As we navigate the intricacies of the Doppler effect, we can appreciate its applications across diverse fields, from astronomy to medicine. Yet, we must also acknowledge the limitations imposed by our environments and the interpretations of those who engage with this remarkable phenomenon. Each frequency shift, each observation, invites us to delve deeper into the nature of sound and light, urging us to seek clarity amidst the complexities that surround us. What does it mean to truly understand the Doppler effect? It is not merely about recognizing the changes in pitch or frequency, but about grasping the profound implications these changes hold for our interpretation of motion and reality. As we continue this journey, let us remain attuned to the challenges that accompany our exploration, embracing the beauty of inquiry while acknowledging the limitations that shape our understanding of the universe. Chapter 9. Teaching the Doppler Effect, Strategies and Examples. In the realm of learning, the Doppler effect presents a unique opportunity to engage students with the wonders of sound and motion. To effectively illustrate this concept in classrooms, educators can employ a variety of methods that stimulate curiosity and enhance comprehension. One powerful approach is through the use of relatable, real-world examples that connect students' experiences to the scientific principles at play. Imagine a child at the playground, hearing the sound of an ice cream truck approaching. As the truck comes closer, the familiar jingle becomes sharper and more distinct. Then, as it passes, the sound shifts to a softer tone, fading into the distance. This everyday experience serves as a perfect entry point for discussing how the Doppler effect operates, fostering an understanding of frequency changes that occur due to relative motion. Incorporating visual aids can also be immensely helpful. Utilizing diagrams that depict sound waves emanating from a moving source, along with arrows indicating the direction of motion, can provide clarity. These visuals can help students visualize how sound waves compress as they approach an observer and stretch as they recede. As they examine these illustrations, students might wonder how these phenomena apply not just to sound, but also to light, linking back to the cosmic dance of stars and galaxies discussed in previous chapters. Engaging experiments can further deepen understanding. One effective activity involves using a simple sound source, such as a smartphone or a speaker, and a moving object, like a toy car. By playing a sound while the car travels toward and away from the observers, students can hear the pitch change in real time. This hands-on experience reinforces the theoretical concepts introduced earlier, making the Doppler effect tangible and memorable. Another engaging demonstration involves a balloon and a whistle. By inflating a balloon and releasing air while a whistle is blown, students can observe the pitch change as the balloon moves past them. This simple yet effective experiment illustrates the principles of sound wave compression and expansion in a delightful way, inviting laughter and wonder. As students engage with these activities, they are encouraged to ask questions. Why does the pitch change? How can this effect be observed in other contexts, such as in astronomy or medical imaging? By fostering a questioning environment, teachers can guide students to explore the broader implications of the Doppler effect beyond the classroom walls. In addition to hands-on experiments, educators can also utilize technology to enhance learning. Online simulations of the Doppler effect allow students to manipulate variables such as speed and distance, providing a dynamic way to visualize the principles at work. These interactive experiences can bridge the gap between theoretical knowledge and practical application, reinforcing the concepts discussed in previous chapters. To further explore the intricacies of sound wave phenomena, educators and students alike can turn to a variety of resources. Books and documentaries that delve into the science of sound and the Doppler effect can provide additional context and depth. Online platforms offer a wealth of articles, videos, and interactive content that can enrich the learning experience. Consider the words of a renowned physicist who once said that the beauty of science lies in its ability to provoke thought and inspire curiosity. By tapping into this curiosity, educators can guide students on a journey of discovery, unveiling the mysteries of sound and motion through the lens of the Doppler effect. As students continue to explore these concepts, they might find themselves drawn to the vast applications of the Doppler effect in different fields. From the medical realm, where it assists in the diagnosis of health conditions, to the technological advancements in radar systems, the implications are far-reaching. Each of these applications serves as a testament to the enduring significance of the Doppler effect in our understanding of the world around us. In summary, the exploration of the Doppler effect through effective teaching strategies not only illuminates the science of sound waves, but also invites students to engage with the wonders of the universe. By employing relatable examples, hands-on experiments, and technological resources, educators can create a rich and immersive learning environment. As students absorb these lessons, they are not merely learning about scientific phenomena. They are embarking on a journey of discovery that connects them to the world in profound and meaningful ways. In the exploration of sound waves and the Doppler effect, educators can also tap into storytelling as a powerful teaching tool. Narratives that weave together human experiences with scientific concepts can captivate students' imaginations. Consider the story of Christian Doppler himself, who, amidst the hustle and bustle of the 19th century world, observed the everyday phenomena of shifting sounds and transformed it into a groundbreaking scientific principle. This narrative not only honors the historical context of the Doppler effect, but also illustrates the idea that curiosity and observation can lead to monumental discoveries. Imagine a classroom where students are invited to share their own stories of sound. Perhaps one recalls the thrilling moment they stood at a concert, feeling the vibrations of music swell and recede as the band played. Another might reflect on the laughter of friends during a game of tag, where the sound of footsteps approached and then faded away with each turn. These personal anecdotes create a bridge between scientific theory and lived experience, reinforcing the relevance of the Doppler effect in everyday life. In addition to storytelling, integrating music into lessons about the Doppler effect can provide an engaging auditory experience. Music is a universal language, and it can serve as an excellent medium for illustrating how frequency changes manifest in different contexts. By playing recordings of sounds that exhibit the Doppler effect, such as passing emergency vehicles or the sound of a train, students can physically hear the pitch changes that accompany movement. This auditory engagement enhances their understanding, allowing them to connect the theoretical aspects of sound waves to real-world applications. To deepen this connection, educators can encourage students to experiment with musical instruments. For example, a simple demonstration could involve a student playing a trombone or a trumpet while moving toward and away from the class. The resulting shifts in pitch can serve as a tangible representation of the Doppler effect, allowing students to physically witness how sound behaves in response to motion. This activity not only fosters comprehension, but also promotes a sense of wonder about the interplay between sound, motion, and music. When discussing the broader implications of the Doppler effect, it is essential to highlight its role in various scientific fields. In addition to astronomy and medicine, the Doppler effect is crucial in the realm of meteorology. Doppler radar systems play a vital role in weather forecasting, enabling meteorologists to track storm systems and predict severe weather with greater accuracy. Picture a captivating stormy sky, where swirling clouds and flashes of lightning create an exhilarating spectacle. Doppler radar helps scientists observe the speed and direction of these weather patterns, much like a conductor guiding an orchestra through a symphony. By understanding how sound waves interact with moving weather systems, students can appreciate the profound impact of the Doppler effect on our daily lives. Furthermore, the Doppler effect has made its way into modern technology in ways that students may find familiar. For instance, smartphones often employ similar principles in their GPS systems, allowing for accurate location tracking based on the signals emitted by satellites. As students navigate through their daily lives, they may not realize that the very technology they rely on is steeped in the scientific principles we are discussing. This connection can spark curiosity, urging students to delve into the science behind their favorite devices and how these principles are applied in innovative ways. As learners explore these connections, they are encouraged to think critically about how the Doppler effect might influence their understanding of the universe. Imagine a young student pondering how the light from distant galaxies reveals the expansion of the universe itself, with redshift indicating objects moving away from us and blueshift suggesting objects in motion towards us. This contemplation can lead to discussions about the nature of space, time, and the very fabric of reality, weaving together concepts from previous chapters. To further aid students in exploring the Doppler effect and sound wave phenomena, educators can compile a list of resources that extend beyond the confines of the classroom. Documentaries on sound and the universe can provide fascinating visual narratives, while online platforms can offer interactive simulations that allow students to experiment with different sound frequencies and velocities. Engaging with these resources can fuel their passion for science and encourage them to pursue knowledge beyond the syllabus. Moreover, the use of educational platforms that host virtual labs can enrich students' understanding of sound wave behaviors. These digital environments can simulate various scenarios, enabling learners to manipulate variables such as speed and distance while observing the resulting changes in frequency. Such immersive experiences not only enhance comprehension, but also cultivate a sense of agency in students as they take an active role in their learning journey. As educators guide their students through these explorations, they foster an environment of inquiry where curiosity flourishes. By encouraging learners to ask questions and seek answers, teachers empower them to engage with the world around them on a deeper level. What other phenomena might reveal their secrets through the lens of the Doppler effect? How can understanding sound and motion transform our perspective of everyday experiences? These questions can ignite a passion for discovery, inviting students to become lifelong learners in the realm of science. Through these varied approaches, storytelling, music, hands-on experiments, and technology, educators illuminate the principles of the Doppler effect and its vast implications. Each lesson becomes an invitation to explore the world of sound and motion, revealing the beauty of scientific inquiry intertwined with the richness of human experience. As students engage with these concepts, they embark on a collective journey of discovery, one that resonates not only within the classroom, but also in the broader landscape of their lives. As educators guide students through the multifaceted landscape of the Doppler effect, they can also encourage a sense of wonder about the natural world. The interplay between sound and movement is not merely confined to classrooms or textbooks. It exists all around us, waiting to be discovered. Imagine a quiet evening where the distant sound of a train echoes through the valleys. The gentle whoosh of air as it passes by might remind students of how their own voices carry differently based on their surroundings. This acoustic phenomenon can be a captivating starting point for discussions about how sound behaves in various environments. To further enrich this exploration, educators might introduce students to the concept of wave interference. Picture two sound waves traveling through the air, their peaks and troughs overlapping. When they meet, they can amplify each other, creating a louder sound, or they can cancel each other out, resulting in silence. This intricate dance of waves can be compared to the blending of colors in a painter's palette, where the outcome depends on the combination of hues. By visualizing sound waves in this way, students can gain a deeper appreciation for the complexities of sound behavior, including how the Doppler effect fits into a broader context of wave mechanics. As students become more engaged with the nuances of sound, they can also explore the role of frequency modulation in everyday technology. Many familiar devices utilize principles of sound waves to function effectively. For instance, consider how wireless communication relies on modulating signals to transmit information over vast distances. Educators can invite students to think about the ways in which the Doppler effect influences their daily lives, from the sounds of their favorite video games to the clarity of phone calls. By making these connections, students can see that the science of sound is not just an abstract concept, but a vital component of the technology they interact with every day. Another thought-provoking aspect to consider is the role of the Doppler effect in environmental monitoring. Scientists employ this phenomenon to study the movement of animals in the wild, tracking their behaviors and migrations through sound. Imagine a researcher in a dense forest, equipped with specialized equipment that captures the sounds of creatures moving through the underbrush. By analyzing these audio signals, they can gather insights into the health of ecosystems and the effects of climate change. This real-world application invites students to consider how sound waves can serve as indicators of broader environmental trends, thereby reinforcing the interconnectedness of science and nature. To ensure that this exploration remains dynamic and engaging, educators can incorporate multimedia resources that showcase the Doppler effect in action. Videos that illustrate the phenomenon through various lenses, ranging from the cosmic shifts of distant galaxies to the swift movements of athletes, can captivate students' imaginations. Each visual representation enriches their understanding while emphasizing the beauty inherent in scientific discovery. Imagine the lights of a bustling city captured in slow motion, where the sounds of traffic rise and fall in a rhythmic symphony. Such imagery can serve as a powerful reminder of how science permeates our everyday experiences. As students delve deeper into the world of sound waves, educators can encourage them to share their findings and insights. This collaborative approach fosters a sense of community and allows students to learn from one another. Imagine a classroom buzzing with excitement as students present their unique experiments or findings related to the Doppler effect. Each presentation becomes an opportunity for inquiry, igniting discussions, and prompting new questions. What other phenomena can be explained through the lens of sound? How can understanding these concepts lead to innovative solutions in technology or environmental conservation? Through these methods, the teaching of the Doppler effect transforms into a journey of exploration, reflection, and creativity. By actively engaging with the material, students not only grasp the scientific principles at play, but also develop a profound appreciation for the interconnectedness of science, technology, and the natural world. As they continue to uncover the mysteries of sound, they embark on a path of lifelong curiosity, equipped with the tools to question, explore, and innovate. Chapter 10: Future directions, advancements in Doppler technology. As we stand on the cusp of a new era in sound wave analysis, emerging innovations promise to enhance our understanding of the Doppler effect and its many applications. Imagine a world where the subtle shifts in frequency can be harnessed to unveil secrets of our universe, and where technology empowers us to explore realms of knowledge previously thought unattainable. With advancements in digital signal processing and machine learning, researchers are developing new techniques for analyzing sound waves that could redefine our approach to the Doppler effect. One exciting innovation is the integration of artificial intelligence in sound wave analysis. Through sophisticated algorithms, machines can now recognize patterns in sound waves that were once imperceptible to the human ear. This enhancement allows for a more nuanced interpretation of the Doppler effect, providing deeper insights not only in astronomy and medicine, but also in fields such as environmental monitoring and even wildlife conservation. For instance, consider the application of these technologies in tracking the movements of endangered species. By analyzing the sounds produced by these creatures, researchers can determine their location and behaviors, fostering conservation efforts that were previously hindered by limited observational techniques. Imagine listening to the symphony of nature, where every rustle and call is a note in a grand orchestral piece. With the ability to finely tune our analysis of these sounds, we could decipher the intricate communications of animals, learning how they interact with their environment and with each other. This emerging field of bioacoustics is a testament to the potential of sound wave analysis, reshaping our understanding of ecological dynamics. As we reflect on potential future applications, the impact of technology on understanding the Doppler effect becomes increasingly evident. Think of the medical field, where the precision of Doppler ultrasound is being enhanced by advanced imaging technologies. Innovations such as three-dimensional imaging and real-time visualization are revolutionizing how clinicians assess blood flow and cardiac function. Picture a doctor, equipped with these advanced tools, able to visualize the flow of blood in a patient's heart with unparalleled clarity. This not only aids in accurate diagnosis, but also allows for personalized treatment plans, ultimately improving patient outcomes. Moreover, the advancements in Doppler radar technology are expanding our capabilities in weather forecasting and climate science. Imagine meteorologists equipped with high-resolution Doppler radar systems that can detect minute changes in atmospheric conditions. This level of detail can lead to more accurate predictions of severe weather events, providing vital information that can save lives and protect communities. As we harness these technologies, we move closer to a future where the Doppler effect is not just a scientific curiosity, but a tool for safeguarding our planet. In the realm of space exploration, the potential applications of Doppler technology continue to grow. With the advancement of space telescopes, astronomers are now able to analyze the light from distant galaxies, applying the Doppler effect to understand their velocities and trajectories. Imagine standing on Earth, gazing up at the night sky, and knowing that the light from those distant points is telling a story of cosmic movement. This narrative extends beyond our galaxy, offering insights into the very fabric of the universe. As we delve into the realms of exoplanet discovery, the Doppler effect plays a crucial role in identifying planets orbiting distant stars, providing evidence of their existence through the subtle shifts in light they produce. The impact of technology on our understanding of the Doppler effect is profound, yet it also raises intriguing questions about the nature of perception itself. How much of what we perceive is shaped by the tools we use? The evolution of sound wave analysis invites us to ponder the relationship between technology and human experience. As we enhance our ability to interpret frequency shifts, we gain not only knowledge, but also a deeper connection to the world around us. Reflecting on the journey of the Doppler effect, we find ourselves at a pivotal moment in scientific history. Each advancement in technology opens new avenues for exploration, and as we look to the future, the possibilities are as vast as the universe itself. Imagine standing at the threshold of discovery, where the mysteries of sound and motion beckon us to explore further. In this context, the Doppler effect becomes more than just a scientific principle. It becomes a bridge connecting us to the cosmos, to the intricate workings of life, and to the very essence of our existence. As we embrace these advancements in sound wave analysis, we may find that our understanding of the Doppler effect continues to evolve, reflecting the dynamic nature of science itself. The journey of exploration is ongoing, and each new discovery adds to the rich narrative of our quest for knowledge. As we contemplate the future, we are reminded of the words of a notable scientist who once said, "Science is not only compatible with spirituality, it is a profound source of spirituality." With each advancement in Doppler technology, we are not merely expanding our scientific toolbox, but also deepening our appreciation for the interconnectedness of all things. Thus, the future of Doppler technology is not limited to the confines of scientific laboratories or academic institutions. It is a shared journey, inviting collaboration and curiosity across disciplines. As we continue to innovate and explore, we will uncover layers of understanding that transcend our current knowledge, illuminating pathways to new discoveries yet to come. Imagine the stories that await us, stories of sound, movement, and the infinite possibilities that lie ahead. As we explore further into the potential future applications of Doppler technology, we find ourselves at the intersection of innovation and necessity, where the implications of these advancements resonate across various scientific fields. Consider the realm of environmental science, where understanding the nuances of sound waves can lead to breakthroughs in monitoring ecosystems. The intricate sounds of a forest, from the rustling leaves to the calls of wildlife, play a crucial role in maintaining ecological balance. With advancements in sound wave analysis, researchers can deploy acoustic sensors throughout diverse habitats. These devices listen attentively, capturing the symphony of life around them. Imagine a network of sensors embedded in the heart of a rainforest, each one collecting data on the frequencies of animal calls and the sounds of plant life. By analyzing these sound patterns, scientists can discern the health of an ecosystem, identifying changes that may indicate environmental stress or the presence of invasive species. This innovative approach not only enhances our understanding of biodiversity, but also informs conservation strategies that are vital for preserving our planet's delicate balance. In the field of agriculture, Doppler technology offers promising solutions for improving crop management. Picture drones equipped with advanced sound wave analysis systems soaring over fields, collecting data not just on plant health, but also on the presence of pests or diseases. By analyzing sound frequencies emitted by crops, farmers can gain insights into their vitality, enabling timely interventions that enhance yield and minimize waste. This application exemplifies how the Doppler effect can serve as a catalyst for sustainable practices, ultimately contributing to food security in an ever-growing world. Turning our gaze to the world of engineering, we see the potential for Doppler technology to revolutionize structural health monitoring. Imagine towering bridges and skyscrapers, fortified by a network of sensors that continuously analyze the sound waves generated by stress and strain. This real-time monitoring can provide valuable information regarding the integrity of structures, allowing engineers to detect potential failures before they occur. The integration of Doppler technology into infrastructure not only ensures safety, but also extends the lifespan of our built environment, a crucial consideration in our rapidly urbanizing world. Another avenue for exploration lies within the exciting realm of virtual reality and augmented reality. As these technologies continue to evolve, the incorporation of sound wave analysis can enhance immersive experiences in ways we have yet to fully imagine. Picture stepping into a virtual world where every sound is meticulously crafted to reflect the Doppler effect, creating a more authentic and engaging experience. Whether it is the subtle shift in pitch as a virtual vehicle approaches or the delicate nuances of a distant thunderstorm, the application of Doppler principles can transport users into vibrant, lifelike environments. The interplay of technology and the Doppler effect also invites us to consider the ethical implications of such advancements. As we develop more sophisticated tools to analyze sound waves, questions arise about privacy and the potential for misuse. How do we balance the benefits of monitoring and analysis with the need for individual freedoms? The ability to listen to the world around us is a powerful tool, and with it comes the responsibility to wield that power thoughtfully and ethically. The impact of technology on our understanding of the Doppler effect extends beyond practical applications. It also fosters a broader philosophical discussion about the nature of sound and perception. As we enhance our ability to analyze and interpret sound waves, we begin to uncover the layers of meaning embedded within them. How do our interpretations of sound shape our experiences? The advancements in sound wave analysis encourage us to listen more deeply, to appreciate the subtleties of communication that exist in our everyday interactions. Consider the world of music, for example, where the Doppler effect plays a pivotal role in our auditory experiences. As musicians perform, the movement of their bodies and instruments creates a dynamic interplay of sound that resonates with audiences. Imagine a symphony orchestra, where each musician's position influences the perception of sound. The nuances of frequency shifts impart a unique quality to the performance, engaging listeners in a profound dialogue between artist and audience. This interaction not only enriches the musical experience, but also reinforces the idea that sound is an ever-evolving medium shaped by motion and context. As we look to the future, the advancements in Doppler technology also hold promise for education. In classrooms around the world, educators can leverage these innovations to engage students in the wonders of sound and wave behavior. Imagine students experimenting with sound wave generators, observing firsthand the changes in pitch as they manipulate the distance between the source and the observer. This hands-on exploration fosters a sense of curiosity and wonder, instilling a love for science that may inspire the next generation of innovators. In this context, the Doppler effect transcends its scientific origins, serving as a gateway to understanding the interconnectedness of all things. With each advancement, we are reminded of the beauty that exists in the patterns of sound and motion, inviting us to explore the depths of knowledge with open hearts and minds. As we embrace the future of Doppler technology, we find ourselves not only uncovering new scientific insights, but also nurturing a profound sense of connection to the world around us. The journey of discovery is far from over, and the possibilities that lie ahead are as expansive as the sound waves that ripple through the universe. Each new innovation invites us to listen more closely, to understand more deeply, and to engage with the rhythm of life that surrounds us.